How's everybody doing? Exam this week? Everybody had a chance to look at the videos I provided? Protein charge, okay. Clear as mud? Approximately? Slightly clearer than mud, I hope. Okay. Well, if you have questions, come see me. I'm more than happy to help you, and the TAs are more than happy to help you as well. So use the resources available to you. Yes? Yes. Okay. Okay. I thought the transparencies were from the video. Are they not matching the video? Oh, I'll have to take a look at that. I apologize. I didn't realize that. So maybe I grabbed the wrong one. There's no match at all? Huh. Okay. Thanks for letting me know. I'll take a look at that. I will, as I said, I'm happy to meet with people if you have questions about stuff as well. So I will look into that, though. But thanks for letting me know. I'll check on that tonight. Okay? Okay. Well, I haven't decided exactly where I'm going to cut off the material. It will be somewhere around here on enzymes. There was an old link on the schedule page that said it was going to cut off at the end of this lecture. It might, but I haven't decided that for sure. I will let you know, and we'll decide where we're going to go with things, okay? All right. So we're talking about enzymes, and though it looks like there's just a little bit of material there, there's actually a fair amount of things to talk about within that material. So I want to spend some time going through that with you. And as I said, I like to think about things in practical terms. So I will talk about things in terms of conceptual things about how enzymes work and try to relate them to mathematical terms that other people use. Okay? So we're going to try to grab this and understand this as concepts, and I think that's the most important way that we can understand enzymes. Okay? Well, last time I talked about the considerations of energy. Here's another way of looking at an enzymatic reaction with respect to energy, and so I want to just say a few words about that. So this is a little bit more elaborate of a diagram showing how an enzymatic reaction progresses. We have an enzyme labeled as E, and we have a substrate. The substrate is the thing that the enzyme binds and catalyzes a reaction on. That substrate might be one molecule, it might be two molecules, it might even be three molecules. Okay? But for our purposes, we're just going to keep it simple and just call it substrate. Okay? Out here we have E plus S, meaning they haven't bound to each other yet. Over here we have E bound to S, and we see that the binding of E to S is favorable. That is that we see a drop in energy associated with that. We have an energy hump we have to get over, but we have a product that comes out here. And the point that I made the other day about the overall energy not changing was this. If I do this whole process and I have no enzyme, and I had substrate and I had product, we might see a bunch of different squiggles going up and down and so forth in the middle here. But the starting energy of the substrate and the final energy of the product would still be the same. Enzymes do not change the overall energy. Okay? Enzymes do not change the overall energy of a reaction. The only thing that they change is the transition state energy. Okay? Now, we could spend quite a bit of time talking about what transition state really means, okay? But transition state is just simply, we could think of as an activated state where the reaction starts to occur. And I think if we leave it in those simple terms, that's really all you need to know about a transition state for a reaction, okay? It's just an activated state where the reaction starts to occur, okay? So you may see in various places, you'll see this E plus S, you'll see this ES. This means they're bound together and you haven't made anything yet, okay? You're in the process of making it here, and here's the final product over here. That's sort of just a schematic diagram showing you the steps in that process. Okay. Well, let's look at some specific examples. Okay. So Some specific examples, one of the most common specific examples we start with are a class of enzymes that we call the serine proteases. Serine, just like the amino acid serine, and proteases, like the enzymes that break peptide bonds. We talked about proteases like trypsin. We talked about chymotrypsin. Okay? These are enzymes that catalyze the breakdown of other proteins, and they do that by breaking peptide bonds. Chymotrypsin is one of those. Okay? So, actually, let's see what I had. I don't want to go through that. All right. So here's chymotrypsin. Okay? What am I looking at here? All right. Well, what I've done is I'm following a reaction by measuring the velocity of the reaction compared to the substrate concentration. So I want to say a few words about this. All right. This is a very common plot that we make with respect to enzymes. So I want to tell you how we make it, because it's important for you to understand how these things are generated. And then we'll talk about some relevant features of this plot that you see on the screen. Okay? This looks a lot like that hyperbolic plot that I showed you for myoglobin binding to oxygen. I said that was hyperbolic. It just went up and then it flattened out. Okay? All right. So what does this tell us? All right. Well, first of all, let's talk about what is reaction velocity. All right? Velocity. When I say velocity to you, that means has something to do with how fast you're going, and how fast you're going is a rate. It's a rate based on how far you travel divided by how long it takes you. The higher that ratio is, the faster you're traveling. If you're going 60 miles per hour, there's the rate. You're going faster than you are if you were going 30 miles per hour. If you travel both of those the same amount of time, you will, in fact, travel farther at 60 miles per hour than you will at 30 miles per hour. Okay? Well, what does velocity mean for an enzymatic reaction? It's not going anywhere. It's not moving. So why do we use the term velocity? All right? Well, velocity for an enzymatic reaction is measured, not surprisingly, as a function of how much or how fast we're making product. How fast are we making product? Okay? That's what a reaction velocity is all about. How fast am I making product? Okay? Now, it's slightly confusing. We're not going to worry about it too much for our purposes, but I want to give you the definition of what velocity actually means. Okay? It's not the quantity of product, although indirectly it is. It's not the quantity of product that we make. It's the concentration of product divided by time. So velocity is measured as the concentration of product divided by time. So there's that time component, just like we saw in the velocity when we're driving down the road, 60 miles per hour. In this case, we might be having 0.1 molar per minute, okay, just as an example. Okay? Molar being the concentration, minute being the time. Yes?
Can I say it's the accumulation rate?
It's a what?
Accumulation rate?
It is. I would say no, it's not an accumulation rate because reactions go backwards as well as forwards. So you will see with time it will accumulate, but it will also stop because it will reach equilibrium. So it's not really an accumulation rate now. Okay? Okay. So velocity is the concentration of product per time. Now let's think about a reaction that goes, and I'm going to answer her question over here also to illustrate what I'm talking about. It's not really accumulation, because things don't really accumulate as such. All right? Let's imagine I have a reaction A goes to B. A could be one molecule, B is another molecule. And we're interested in measuring the rate with which A converts to B. Okay? Well, if all that happened was that A went to B, we would have an accumulation rate. We just look at the rate of accumulation of B and we would have it. But I want you to remember something. All reactions, including all enzymatic reactions, are reversible. They are reversible. So just as I have A going to B, I will also have B going to A. Right? Now that turns out to be important, especially the longer I let the reaction go. All right? if I let a reaction, let's say I start only with A, and I start measuring the rate of appearance of B as measured by the concentration of B per time, that would be a velocity, okay? Then I'll see it's going to take off, and then what's going to happen is the rate is actually going to slow down. And the rate's going to slow down because as B starts to accumulate, it starts being made back into A. Okay? So if we want to measure the velocity of this reaction, we want to measure something called initial velocity. We measure the velocity before B has a chance to accumulate. The more B accumulates, the more of the reverse reaction is going to be favored, and the less accurate my estimate of the velocity is going to be. Okay? Now, one of the things that you didn't learn in freshman chemistry was largely a fault of the people teaching freshman chemistry. I won't blame you. But one of the things that they didn't really teach you very well in freshman chemistry was the notion of what equilibrium is. For probably 75% of you in here, equilibrium means equal amounts of reactant and product. And that's completely wrong. Okay? It's not equal amounts of reactant and product. Get that in your head. Okay? Equilibrium is a state where the rate of formation of reactant and product are the same. That might be at a ratio where we have 10 times as much A as B. It might be where we have 5 times as much B as A. It's going to be different for each reaction. But when they reach that point where their concentrations no longer change, they're at equilibrium. That is what equilibrium is, not equal amounts. Okay? All right. So if we wait till we get to equilibrium, what we will see is no velocity, because there's nothing going forward, because the concentration going forward is the same as the concentration going backwards. We see nothing happening. So it's important that when we measure velocities, we measure initial velocities. We start out with all A and no B, and we only measure it for a very short period of time before the B has a chance to accumulate. Okay? Okay. Don't want to get any more technical than that. Well, how did I generate this plot? Well, here's a substrate that, it's actually an artificial substrate, but this is a substrate that chymotrypsin is catalyzing a reaction on. All right? It looks like a peptide bond to the chymotrypsin, so it treats it like one. Okay? What happens is this. How would I do an experiment to measure the velocity versus the substrate concentrations? Well, here's what I would do. I would take 1, 2, 3, 4, 5 different tubes, each of which had a specific amount of substrate. There's the amount for the first one, there's the amount for the second one, there's the amount for the third one, the fourth one, and the fifth one. So I have 5 different concentrations of substrate that I start with. Each tube then gets the same amount of enzyme. So I put X amount of enzyme in number 1, X amount of enzyme in number 2, X amount in 3, X amount in number 4, X amount in number 5. And then I let each one go for exactly the same period of time, and then I measure the concentration of the product. Well, what this is telling us is that the more substrate we have, the faster the velocity. The more substrate we have, the faster the velocity. That makes intuitive sense. All right? Well, let me give you a real-world example. Real-world example, okay? Let's say that I'm working at General Motors and I am producing cars. And I have a factory that is producing those cars. All right? Cars get made as a result of parts being assembled, raw materials being put together, and the final product is a car. Okay? And workers. I have to have workers, right? Well, if the workers are the enzymes, and I have a fixed amount of workers, and I start out a day at the factory where I have only a few parts available, I'm not going to get very many cars out, right? Because soon those workers, if they're very efficient, they're going to put the parts together, they're going to make a car, and they're going to run out of parts, and they're going to wait for more parts. Right? Well, the parts are the substrates. The parts are the substrates. If I take the next day and I take the same number of workers and I have twice as many parts and I put the workers to work, they're going to make more cars than they made the first day. Right? And I take the third day and I have 3 times as many parts, etc. Well, does it just keep increasing? Well, it's not going to, because the first day the workers are twiddling their thumbs for part of the day. The second day, they're twiddling their thumbs for a little bit of the day, but not as much. And by the third day, well, we better hurry up and get these cars out of here. The fourth day, we're starting to see, whoa, man, this guy's working us to death because all I'm doing is making cars, and I'm getting up here, and I'm saying on the fifth day, geez, all I did all day long was make cars. I didn't get a chance for a coffee break. I had to work overtime. I had to do my thing. All right? We see the curve actually flattens out. What we're doing in the case of the car factory is we're saturating the workers. They have a fixed amount of cars that they can put out. No matter, I could put 300 times as many parts there, but after a point there's only going to be so many cars they're going to have time to put out in a day. An enzyme is exactly the same way. An enzyme, if I keep adding substrate to it, at first, yeah, that's great, more, but finally I start saturating the enzyme with substrate. Okay? When I saturate the enzyme with substrate, I reach a point that we call Vmax. That stands for maximum velocity. And on this curve it would be about right here. About right there would be Vmax. So if I said what's Vmax, it would be right there as it went over to that point. Okay? Vmax is interesting, Vmax is useful, but as I emphasize to students, Vmax is not a constant that's characteristic of an enzyme. It's not. Now, that may not make much sense to you at the moment, but I'll tell you why I say that. Okay? Let's go back to the General Motors example. If I do my factory and I have my workers and I have them working at capacity, as I said, it doesn't matter how much more parts I bring, the workers are only going to put so much out, right? But what if I start another factory with another batch of workers next door? I've just doubled capacity, right? And so now all the parts that were going to just the one are going to the two. Wouldn't you expect that if I doubled the number of factories and everything else was equal, I would be doubling the number of products being made? Right? The same is true of an enzyme. If I use twice as much enzyme, I would expect that I would get twice as much of each one of these. So Vmax is not a constant. It varies depending on how much enzyme I use. Vmax depends on how much enzyme I use. So I can't compare Vmaxes. Let's say, and people like to do this, they say, what's the Vmax of that enzyme? Well, I can tell you the Vmax under the conditions I measured it, but that you can't compare it to the Vmax of your enzyme because maybe you used a very different amount of enzyme. Right? We want to be able to compare the rates of two different enzymes. But Vmax is not the way to do it because Vmax depends on how much enzyme I used. Does that make sense? Yes?
Would it also depend on the environment of the enzyme?
It will, but if we assume that the two environments are the same, then that's going to be all equaled out, right? It will, yes. Okay? Just like the weather might affect how productive an automobile factory might be, right? Maybe its parts are rusting or something, or I don't want to go out in the rain and pick up that bumper and come back in. You go do it, right? Okay. So what do we have to have then? Well, we don't compare enzymes with Vmax, but we still want to compare velocities. How do we do it? Well, if we knew how much enzyme we used, we could take that into account, right? What we do is a very cool trick. We take, remember that the velocity is the concentration of substrate divided by time, right? So Vmax is going to be a concentration of substrate divided by time. It's going to be the largest one of those. If I take Vmax and I divide it by the concentration of enzyme that I used, now I've taken enzyme concentration into consideration. I've taken it into consideration. I've created a new quantity, and that new quantity we call Kcat. K and then the subscript CAT. The catalytic constant is what it is, but Kcat is all you need to know. Kcat is also called the turnover number, which sounds very good in the morning when you're hungry. That's a joke. Slow class today. Monday classes never get jokes, you know. Monday classes are just sitting there going, shut up and let's get out of here. It's 5 o'clock, right? What's that?
Slower.
Just slower. The coffee has worn off already. You had a big batch this morning and it's just not going today. Is that right? Bear with me. That's all I can say. Okay, so Kcat. So Kcat I can compare. I can say, what is the Kcat of that enzyme and what is the Kcat of this enzyme? And I can say, my enzyme is higher than your enzyme. My enzyme works faster than your enzyme does. Now, Kcat gives us a very interesting number. Okay? We're taking a concentration, which is the concentration of products, and we're dividing it by another concentration, which is the concentration of enzyme. The two concentrations actually cancel out. So what we get is a number per time. I might get 100 per second. What does 100 per second mean? It means 100 molecules of product per molecule of enzyme per second. It tells us how fast each and every single enzyme is working in that solution. Okay? That's all arising from this plot right here. I'll repeat that, yeah. So the turnover number, or the Kcat, is a number divided by time. It might be 100 per second. And if I had 100 per second, it would mean that every molecule of enzyme in that solution is making 100 molecules of product per second. Okay, so it's because of that I can compare two different enzymes. This enzyme is producing 100 molecules of product per second. This enzyme is producing 500 molecules of product per second. This enzyme is faster. Okay? I can't do that with Vmax because Vmax goes up and down as I change the enzyme concentrations, but Kcat takes that into consideration. Okay. Now, I'm going to come back to ATCAs in a minute. You don't need to worry about that. This is trying to explain what you saw in that last graph, okay? But suffice it to say, it's hyperbolic. It goes up and it flattens out, and it's flattening out as it's getting saturated, okay? So we don't need to worry about the explanation for that graph right there. Yes?
Is the Kcat in enzyme depends only in the concentration or also in the types of enzyme? Like enzyme 1 is better as a catalyst for this reaction than enzyme 2.
Okay, so the question is, does Kcat depend on the concentration of enzyme, I think was the first question. And the second question was, will you have some reactions where one enzyme is better than another enzyme for the same substrate? Is that what you're saying? Okay. So the answer to both of those is, in the first case, Kcat is independent of enzyme concentration. We've taken that concentration into consideration when we divided by the enzyme concentration. So Kcat is a constant. That's why I say it's a constant for an enzyme. It doesn't matter how much enzyme I use to find it. It's always going to be the same number. Okay? So that's one consideration. With respect to the second, yes, there are sometimes more than one enzyme that will work on the same substrate. But I don't want to, but they also may make different products too. So I don't want to go there and confuse that issue. So let me leave that for later, okay? Okay. All right. Now, let me show you another parameter, then I'm going to come back and talk about ATCAs. All right? Here's the same plot you saw before. Okay? Here's Vmax. It's about the place where this guy flattens out. It's a little high, but it's actually somewhere out in here. Maybe Vmax is right there. We'll see. But anyway. Now, this shows another quantity on here that is useful for us to understand about enzymes. The first thing we were interested in understanding about enzymes was how fast they worked. And Vmax gave us an estimate of that. Kcat gave us a much better estimate of that. Right? Both had to do with speed, but Kcat was the better one for comparing speeds. All right? Another thing we would like to know about enzymes is how much does the enzyme have affinity for, there's that word again, its substrate. How much does it like to bind to its substrate? Now, you've heard the word affinity previously when I talked about hemoglobin. With hemoglobin, I said the affinity was the strength with which it bound to the oxygen, right? And hemoglobin is not an enzyme. It just binds and lets go of oxygen. It doesn't do anything to it. It just grabs a hold of it, lets go of it, grabs a hold of it, lets go of it. Okay? It acts a little bit like an enzyme in that enzymes also grab a hold of things, but enzymes are different in that enzymes grab a hold of things, they do something to them, and then they let go of them. Okay? So hemoglobin is not an enzyme, but an enzyme is. So we want to know, just like we wanted to know for hemoglobin, what's the affinity. And with the case of an enzyme, we can measure that affinity pretty readily. Okay? Well, how do we do it? Well, we do a V versus S plot that we did before. There's velocity, there's the substrate concentration. Okay? And we get our hyperbolic plot, and we get this approximate Vmax, wherever this Vmax is up here. Okay? And then we say, well, what was the substrate concentration that it took to get half of Vmax? That turns out to be useful for us. I'll explain why in a second. Okay? Well, here's Vmax. We take Vmax, we cut it in half. Here's Vmax over 2. And with the substrate concentration it takes to get Vmax over 2, we get by reading off of the graph. We go to the line, and we read down. And there, that quantity right there is called the Km. The Km is, first of all, it's a substrate concentration. And specifically, it is the substrate concentration that it takes to get to half of Vmax. Now, why do we pick the substrate concentration for half of Vmax? Why not take the substrate concentration for Vmax? Well, the answer is because, in theory, the substrate concentration it takes to get to Vmax is infinity. Because you notice this thing flattens out, but you guys know from doing your math and calculus and so forth that when curves flatten out, we get tangents, and they keep incrementally going up, 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 up. Okay? An infinite amount of substrate doesn't tell us anything. Right? But if we look at the substrate concentration it takes to get to half of Vmax, that is to get that enzyme, I like to describe the enzyme as being woken up. The enzyme is sitting here sleeping. We wake up the enzyme by getting it half active. It's kind of like maybe you are in the morning before you've had coffee and cereal, right? You're half active at that point. What does it take to get your attention at that point? Okay? This is the same thing that's happening here. Now, let's think about what this term tells us. Okay? Km. Km actually tells us how much the enzyme likes to hold on to the substrate. It is a constant for an enzyme. Okay? Km is a constant for an enzyme. I can compare Kms of different enzymes. And they will tell me something. How will we interpret the Km of an enzyme? Let's imagine I have the situation that she described over here, where I have two enzymes that bind to the same substrate. But they're different enzymes. Okay? And I want to say, does this enzyme over here have a greater affinity than this enzyme over here does? They might very well have different velocities. But I want to know, do they have different affinities for each other? I would compare their Km values. I want to compare their Km values. Let's say enzyme over here, number 1, has a Km value. Remember, it's a concentration of 0.01 molar. 0.01 molar, right? And let's say the enzyme over here, enzyme number 2, has a concentration of has a Km of 0.05 molar. That means the first enzyme, 0.01 molar, got it to half Vmax. The second enzyme, 0.05 molar, got it to half Vmax. Which one likes the substrate more? Enzyme 1 or enzyme 2? Enzyme 1. Okay? The enzyme 1 liked it more because it took less substrate to wake it up. It started grabbing it very quickly. The other one over here took a lot more coffee to get woken up. It took 0.05 molar to do it. So Km, a high Km value means low affinity. A low Km value means high affinity. Okay? So the Km we can think of as the affinity of the enzyme for the substrate. It's a very useful thing for us to understand. Okay, now, I'm not taking any questions, at least I haven't been. I will stop here and take questions that you might have about what I've been saying. Yes? Can I go over how I got KCAT? Yeah. KCAT I got was in a very simple way. I went and I did my reactions. I determined what my Vmax was. And I divided Vmax by the concentration of the enzyme I used in all the reactions. Because remember, I used the same concentration in each one of those 5 reactions. Yes?
Could you go over what you mean by affinity as it's related to Km?
Okay, so can I go over what I mean by affinity as it's related to Km? I think you're talking about the very last thing I said, where that a high Km value means low affinity. A high Km value means that the substrate has to be banging on the enzyme before it wakes up and starts getting to half Vmax. Okay? A high affinity means low Km. It doesn't take very much for the enzyme to start grabbing it and starting the reaction being catalyzed. High Km, low Vmax, low Km, high Vmax. Yes?
I'm wondering what is the relations between the Km and the half-life of the enzymes?
Okay, so question, what's the relationship between the Km and the half-life of the enzymes? There is none. None. Yep. Okay. So the half-life of an enzyme is really a product of a variety of things. They may include how many disulfide bonds, what are the kinds of interactions that are there, how stable is the secondary structure, how stable is the tertiary structure. So there's many, many variables that will affect that. Okay? Okay. So let's go back and look at another enzyme. Okay? This enzyme is called ATCase. Right? ATCase has a plot that looks like that. When you plot V versus S for ATCase, you see something that looks like a sigmoidal plot. Where have you seen a sigmoidal plot before? Hemoglobin, right? Hemoglobin differed from myoglobin. Hemoglobin had a sigmoidal plot. It had different binding affinities for oxygen. Myoglobin had a hyperbolic plot. It didn't have varying affinities for oxygen. Okay? Now, this looks like a sigmoidal plot. What would this tell you about this enzyme compared to chymotrypsin? Any thoughts? What was the difference between myoglobin and hemoglobin? What'd you say?
Binding sites.
Binding sites. Okay. You may remember that the hemoglobin exhibited a phenomenon we called cooperativity. The binding of the oxygen to one site affected the binding to the second, affected the binding to the third, affected the binding to the fourth, right? ATCase turns out to have multiple subunits, and the binding to the first one affects the second one, affects the third one, affects the fourth one, affects the fifth one, there's actually 6 different binding sites. Okay? All right. So what we're seeing is what looks like cooperativity in hemoglobin. Hemoglobin was not an enzyme. We call that phenomenon cooperativity. In an enzyme, we call that phenomenon allosterism. A-L-L-O-S-T-E-R-I-S-M. Allosterism is the enzyme equivalent of cooperativity. Now we're going to see allosterism happen in a variety of ways. Okay? Cooperativity we only saw happen in one way. That was as the oxygen concentration changed, the cooperativity changed. That's what gave us the sigmoidal plot. Okay? With enzymes we discover that there's several things that can affect the enzyme's activity. Several things. Not all enzymes are allosteric. That is, they don't all exhibit allosterism. But the ones that do are important regulators. They're important ways for the cell to control an enzymatic reaction. Very important. Okay? So allosteric enzymes I like to think of as stop signs on the highway. Right? They are regulators of traffic. The traffic in the cell that we're talking about is not a car driving down the lane, but it is the synthesis of molecules. We use velocity as a measure of the synthesis of molecules, right? We are using allosteric enzymes to control the synthesis of molecules, controlling velocity, as it were. Okay? We will see later when we talk about metabolism, which are the reactions that go on inside of our cell, that we don't just have one reaction going off by itself and that's it. We have a molecule A that's made into a molecule B, and a molecule B that's made into a molecule C, and a molecule C that's made into a molecule D, and a molecule D that's made into a molecule E, etc., etc., etc. We have just made what we call a pathway. Now, tomorrow I will talk about the regulation of those pathways, but I'll give you a little preview. If I stop any one of those reactions from going, I stop the whole pathway. Stopping any one of those stops the whole pathway. That turns out to be a really powerful feature. Just like a traffic jam on I-5 backs up traffic for everybody on I-5 going north, okay? So too will a enzyme being blocked in the middle of a pathway stop everything else from passing through that pathway. And just like some of those cars are going to try to get around that block on I-5 and go alternate routes to get to where they're going, so too will molecules go around other enzymes and do that as well. Very good analogies to pathways. Okay, so this enzyme that we see, ATCase, we'll talk about later, but it is a very important regulatory enzyme because it is allosteric. There are many ways, several ways, I shouldn't say many, but there are several ways of regulating enzymes. Allosterism is one of them. Okay. Now, I'm going to turn to one other thing before I talk about inhibition, and then I think this will be. I will stop for the thing. Actually, before I do, let me show you the KCAT. So here's KCAT. So I've been talking about different enzyme rates, turnover numbers, right? I gave you one of these the other day, carbonic anhydrase. I said a carbonic anhydrase will produce 1 million molecules of product per molecule of enzyme per second. Absolutely a remarkable thing. Here's catalase that works even faster. It goes 40 million per second. There's no way I can make 40 million cars per second. I don't care how fast any automotive factory sets up. There's no way I can do that in the macroscopic world. In the microscopic, nanoscopic world of molecules, these things are possible. Okay? That's a remarkable set of things. But I could say that catalase is an enzyme that works more rapidly than does carbonic anhydrase. I could say carbonic anhydrase is more rapid than acetylcholinesterase, etc. I can compare these. You might go down here and say, well, here's lysozyme. It's really slow, right? Well, that's still not bad. How many things per second can you do? Right? Now, one of the things that you see, look at on the right side, you see Km values. This guy's got a relatively high Km. What would you say about its affinity for its substrate? You'd say it's relatively low affinity. Got to bang it, okay, to wake it up. Once you wake it up, by golly, it goes. But you got to add a fair amount of substrate to it to get it to go. Despite what it would look like over here, there's not a relationship between Km and Kcat. There's not a relationship between Km and Kcat. I'll bring it up very briefly because students usually find this interesting. But there's a term that we use talking about enzymes called perfect enzymes. Okay? And they actually exist. Okay? A perfect enzyme. If I said to you, what is a perfect enzyme based on what I've been telling you, I'm guessing you would say it would be an enzyme that has a very high Kcat, meaning it works very, very fast, and it would have a very low Km, meaning it doesn't take very much for it to work very fast. And that would be a definition that most scientists would use of a perfect enzyme. And so what they do is they actually measure the ratio of Kcat divided by Km. They measure that. You don't need to know this. I'm just throwing this out here for you. Okay? They've used that ratio to measure that. And what they discover is that there are many enzymes that when they measure that ratio, they're very, very efficient, but they all tend to get up to about the same number, and then they never get any higher than that. They have very efficient enzymes have very, very high ratio of Kcat to Km, but there's not one that all of a sudden goes, oh, there's another one way up over here. They just level off. They're flat. Why does that happen? It happens because in enzymes like these perfect enzymes, number one, the rate-limiting thing is how fast something can diffuse in water. You can't beat that. The material has got to make it to the enzyme. If it can't make it to the enzyme fast enough, the enzyme's twiddling its thumbs during that time. Just like the factory worker is going to be twiddling his thumbs if the supplies aren't coming in fast enough. That's what happens with a perfect enzyme. Okay? It's waiting for things to come through water. Very limiting factor. Okay? The other thing that happens with perfect enzymes is that any mutations that they suffer create a less perfect enzyme. They really are perfect. They're less efficient if they mutate. They have evolved over evolutionary time to be absolutely perfect. Okay? There's not a lot of things in nature we think of as being perfect. Some enzymes are in that category. Not all enzymes are in that category. Why do you suppose all of our enzymes aren't perfect? It's a philosophical question for you. There's a very real answer for it. A perfect enzyme has very high velocity, very low Km. Enzymes we will see, you see here, can make 40 million of something per second. Cells have to control things. Cells have to control, they don't want to make too much of something, because if they make too much of something, they might make something that is toxic. So one of the reasons cells control enzymes is they don't want them getting out of hand. And what's something that can get out of hand? A perfect enzyme. You don't get an Indianapolis racing car to go to Fred Meyer. Because if you did, you probably would have some collateral damage on the way there. Right? Similarly, if all enzymes were working at breakneck speed, what do you suppose would happen inside the cell? The same problem. Yes?
Perfect enzyme be allosteric controlled.
Will a perfect enzyme be allosteric controlled? Interestingly enough, many of them are not. No. Because you don't have to control the enzyme, you control the enzymes around it. The pathway. If I stop its substrate, I can stop it in the same way.
So the 3D
That's right. Right. Okay? Okay. I got off track there, but I kind of like perfect enzymes. Okay. Let's talk about one other thing. Will actually finish up. I'm going to talk about inhibition on tomorrow, and after inhibition, that's where the exam material will stop. Okay? Today, all I'm going to talk about is the Lineweaver-Burk plot, and then we'll sing a song. Okay? All right. A Lineweaver-Burk plot. Man, you've been showing me a V versus S plot all this time, Ahern, and now you're going to show me another plot. Okay? What is this? All right? This is the same experiment as before. Same data as before. It's just plotted in a different way. Instead of plotting the velocity versus the substrate concentration, I take the value of the velocity and I take 1 over it. And instead of plotting the substrate concentration, I take the value of the substrate concentration and I plot 1 over it. So in essence, what I'm plotting is something we call a double reciprocal plot. It's called 1 over V versus 1 over S. Notice that's a concentration of S. All right? It's also called a Lineweaver-Burk plot. The name is on the previous slide, so you'll get the spelling when I go back to that. Okay? A Lineweaver-Burk plot looks like this. Same data as before, same experiment. I haven't changed this experiment. I just changed how I plotted the data, and you can see very quickly why I did this. When I plotted that hyperbolic plot, I couldn't quite tell where Vmax was, right? I had to guess where that straight line was that was Vmax at the top. With this kind of a plot, I get a straight line because my points are there, 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 there. All right? They line up in a row, and then I can take and I can draw the line all the way down to the x-axis. That's the dotted part. And out of that, I get 2 very useful numbers. One is I get 1 over Vmax as the number where it crosses the y-axis. It's very easy for me to determine what Vmax is because 1 over Vmax is right there. I take whatever this value is, I take 1 over it, and I've got Vmax. The other number that comes out of this that's very useful and very simple is where it crosses the x-axis. That number is equal to minus 1 over Km. I simply take whatever this value is, I take minus 1 over it, and I get the value Km. So with a Lineweaver-Burk plot, it's very easy for me to determine these 2 very important numbers. There's no question about where did that line flatten out. I've already got the information I need from this kind of a plot. Very simple to read. Questions about that? So it's the same data, same information, just plotted in a different way compared to a V versus S plot. No questions about that? Just give you a pop quiz. All right, let's do a song and we'll call it a day. What do you say? This is to the tune of an old song back in the early 60s. I'm old enough, I remember it. It was called Downtown. The name of the song is called Enzymes. Okay? You guys ready? No? Reactions alone can starve your cells to the bone. Thank God we all produce enzymes. Units arranged to make the chemicals change because you always use enzymes. Sometimes mechanisms run like they are at the races. Witness the K-cat of the carbonic anhydrases. How do they work? Inside of the active site, it just grabs onto a substrate and squeezes it tight in an enzyme. Catalysis in an enzyme. V versus S in an enzyme. All of this working for you. Enzyme, enzyme. Energy peaks are what an enzyme defeats, and it's catalysis. Enzymes. Transition state is what an enzyme does great, and you should all know this. Enzymes. Catalytic action won't run wild, don't get hysteric. Cells can throttle pathways with an enzyme allosteric. You know it's true. So when an effector fits, it will just rearrange all the subunits inside an enzyme. Flipping from R to T, enzyme. Slow catalytically, enzyme. No change in delta G, enzyme, enzyme. You should relax when seeking out the Vmax, though there are many steps. Enzymes, Lineweaver-Burk can save a scientist's work with just 2 intercepts. Enzymes, plotting all the data from kinetic exploration, lets you match a line into a best fitting equation. Here's what you do. Both axes are inverted, then you can determine Vmax and establish Km for your enzymes. Sterically holding tight, enzymes. Substrates positioned right, enzymes. Inside the active site, enzymes, enzymes. All right, guys. See you tomorrow.